Hello, my name is John Riddle of Group 2, which includes myself, Adi Adese, Wendy Wang, and Dahi Kim. The course is IE512, which is Applied Linear Regression. So for our project, we chose to use regression analysis to predict PM 2.5 levels in Beijing using weather and time attributes. So first of all, what is PM 2.5? PM stands for particulate matter, which can be solid or liquid droplets suspended in the air. The 2.5 is in reference to the diameter, so the PM 2.5 would be particulate matter with a diameter less than or equal to 2.5 micrometers. There can be both direct as well as indirect formation of these particles in the air. So direct would be things like agricultural equipment emissions, vehicle emissions, fire, volcanic eruptions, things like that, whereas the indirect would be a host of different chemical reactions. So why is it important? One, from just a general pollution standpoint, and then two, specifically due to health risks for humans as well as animals. Most notably would be cardiovascular, age-specific mortality risk, as well as respiratory. We are interested in the PM 2.5 as opposed to some of the other size classes because the 2.5 is small enough to be able to pass through the esophagus and into the lungs and cause these problems, whereas some of the larger classes would not be able to. The causes of PM 2.5 are attributed mostly to human activity, so things like industrial emissions and vehicle emissions. I have weather there as a question mark because that is the question that the group is trying to answer, of whether or not we can use different weather climate variables as well as time to be able to predict the PM 2.5 levels in the air at any given period. So the data we used data from Beijing, China. The response variable was PM 2.5. The predictors we used were things like date, so year, month, day, hour, season, dew point, temperature, humidity, pressure, wind direction, things of that nature. And then the question we're trying to answer is, can we use this real-time weather data to predict PM 2.5 exposure risk? So a person or a family living in Beijing, China can be able to assess the risk of PM 2.5 before going outside and breathing in the air.
Hello, my name is Joel Wang, and I'm going to talk about the analysis of the data set. So from intuition, we believe that all the attributes we have has some relationship with the response variable, which is PM 2.5 US pulse. So we decide to use multilinear regression model to fit the data. So from this graph, we can tell that the multiple R squared is 0.2856, which means we can predict the response variable from some of the attributes, but not all of them, and the model needs to be modified. Then we use the scatter plot matrix of the predictors to look at the relationship between these predictors, and we can tell that a lot of them do not have very strong correlations, which satisfies the assumption of multilinear regression model. And then we run a diagnostic plot for both weather descriptors and time attributes. So from these two plots, we can tell from the residuals versus fitted plot that the data does not have a constant variance, and from the normal QQ plot, we can tell that the data is not normally distributed, which are the problems that we need to solve. Also, for the ANOVA table, the data is not very beneficial because as I said, the data is not normally distributed and does not have a constant variance. So we need to modify the model, and we decide to use log transformation first.
Hi, my name is Dahi Kim, and the topics that I will explain are the log transformation on y variable, which is PM_US.post, stepwise regression, ANOVA, and confidence interval. As Wendy explained before, since the data didn't show any normal shapes nor constant variances, we tried changing the y variable into the logged y variable. After we ran the code, the residual plots showed the line close to the horizontal, and the normal QQ plot also matched much better with the dotted line. Thus, we were able to proceed our tests with our normalized logged dataset. Since we had so many predictors in our dataset, we divided our variables into two categories, in like climate attributes and time attributes. And we checked them by testing stepwise regression, which was the backward elimination. Based on the output, we could conclude that we can ignore the precipitation variable for the climate attributes and ignore the hour variable for the time attributes. We also checked our variables by using ANOVA. This reaffirmed us that we can ignore the precipitation variable for the climate attributes and the hour variable for the time attributes. Since we also wanted to check the confidence intervals, we ran the t-tests for each single predictor variables. For example, we were 95% confident that the mean of the temperature variable is in the interval around 9.858 to 10.187. Also, we are 95% confident that the mean of the month variable in the interval around 2.313 to 2.411.
Hello, my name is Adichie Desai, and I'll be sharing the results and conclusion of our study. As you can see here, this is the parameter estimates table for the time attributes of our study, with the 95% confidence intervals seen in the rightmost column. Each of these values is broken down, and there are also point estimates for a given value. This is the parameter estimates table for our climate attributes. Note that all the p-values were found to be below 2.2 times 10 to the negative 16th, indicating that these values were statistically significant. And the confidence intervals with 95% confidence can also be seen here on the right for each of the climate predictors. So these are the final regression models, broken down by climate as well as time. Note that precipitation in the climate regression model and hour in the time regression model were not included because of the AIC stepwise results as well as the results of the ANOVA. The idea is that this model can be used to predict PM 2.5 level as long as the input predictors are given. So the takeaways. Essentially, we believe that we found a usable model for predicting PM 2.5 levels based on weather and time attributes. PM 2.5 is the result of a combination of weather attributes and not just a single parameter like humidity or temperature alone. Precipitation does not seem to play a significant role in PM 2.5 level. Ideally, this model can be used in Beijing to make PM 2.5 level predictions. In this way, we hope that it can inform health recommendations as well as industry practices by notifying a company whether to start or shut down their industry practices based on the predicted PM 2.5 levels in the atmosphere on that given day. Finally, there are some limitations with the model. Of course, since the data utilized to create the regression was taken from Beijing, the model can only really be used to make correct predictions for Beijing's PM 2.5 levels. That means that application in other locations may not be as accurate or reliable. Although the model will still work and data can still be input, the PM 2.5 output may not be genuinely true for that area. And finally, if unrealistic values are entered into the model, such as a humidity value above 100% or a temperature that's out of the range of the standard model, then the model will still provide a PM 2.5 prediction. However, this value will be incorrect and unrealistic. Finally, these are some references from our study. Thank you very much.